So hello everyone. In the last session we are seeing about the ampere circuital law, and we have also derived the magnetic field due to the hollow wire and the magnetic field due to the solid wire, and we have also seen that what is the difference, okay, between these two. Only the difference is the inside point. Everything for the outside point and the surface, everything is same. That what we have seen, and basically we have understand the ampere circuital law. Now now let us take some example in some cases and let us discuss more about on this. Okay, so see, whatever the thing we have taken a uniform current density. The current density is considered as uniform. Now let us consider a case where the current density is not uniform. For example, let us say we have a solid wire. Okay, so suppose we have a solid wire. I am drawing into some big form. So let us say we have a solid wire. This is a solid wire. Okay, considered it as a solid wire, and the current is going inside. Cross means inside, correct? This is a solid wire, and try to understand how it is keep like. It is keep like this. Okay, the solid wire is going like this. Infinite solid wire. Okay, it is. Let me write, otherwise some people will not able to understand. Infinite solid wire. Okay, the infinite solid wire basically, and the current is going inside. Okay, and one more thing, the current density is a function of r. Okay, some function of r is given. Let us take that function of r is some constant k r. Okay, some constant k into r. Okay, or let take it as journal. Okay, keep it as journal. Okay, then in that case it will be easier for you to do the derivation for any case. Okay, let us take it as journal. Okay, jr. Now our aim is same. We have to find the magnetic field at a distance r. Okay, let us let that r can be anything. It can be outside, it can be inside. Only there will be difference in the limit. Okay, so let me consider a some point r from this is center. What I will do, I will go at a distance x. I will cut a strip. Sorry, I will cut a strip. Whose thickness is dx, and suppose at this point we want to know the field. We want to know the field. Okay, or yeah, suppose let the thickness is some dx, and okay, let is given. So what is the current density in this? J times of x. So if I want to write the magnetic field, how will you write? What is the approach you will use? See, we know ampere circuital law. We have considered some loop, that the loop is like this. I'm taking like this. Okay, or it is better to take like this. Okay, suppose I am taking like this. So I will write close integration of d dot dl, that is mu into I enclosed, mu naught into what is I enclosed. I enclosed will be j times of x into area. Now what is the area of this? That we know how to write the area of this, 2 pi x into dx. So the area will be 2 pi x into dx, and then you have to take b outside, and we have to integrate dl. Okay, now the integration of dl, close integration of dl, should be from where? From c. Now you have to see the x is varying from 0 to x is varying from 0 to what point? It is going to be vary from 0 to whatever the point where you want to find. That is from the up to that point it is varying. So if it is varying from 2 pi small r, that r can be anything. Okay, this r can be inside, outside, it doesn't matter. So you just do this thing. Okay, yes, you have to just do what? You have to just integrate this. Let me check once. Yes, correct only. J times of x, 2 pi x into dx, correct? So we will get how much? This, sorry, let me write it as properly. V naught b into 2 pi r is equal to j of x. Okay, so from here you get b is equal to mu naught. Now the thing is that we have to see, this is a current density which is present in the small thickness, but we have to know the total current na, in this loop. So we have to integrate for this loop, s is equal to 0 to x is equal to how much, whatever the distance we are taking. So then our magnetic field will be how much? After you do this integration, you will get our magnetic field as how much? See, mu naught integration of x is equal to 0 to x is equal to r j of x 2 pi x dx divided by 2 pi r. So that is a magnetic field we will get. So now I can put jx as a function of anything, it doesn't matter. It's a general formula for you. You can treat it as a general formula. But remember, this formula is valid only for this current solid current carrying infinite wire. Okay, else case it is not valid. So you have to just put the function of gx and just you integrate, you will get the correct magnetic field whatever at that point. Clear? So this is how we can do for the general case. Okay, just I have given you the idea of this. Clear? It's an example. Okay, it's example and it's an idea for you. If any general case will come with a function of some j as a function of r or x, you can do that, okay, by using this concept. Clear? Any doubt till here? Please note it down first. Completed? Any doubt? Okay, so let us take one example. If you don't have a doubt, let us take one example. Okay. Example is simple. It's basically saying, let us consider two circles. Let us consider the two circles. Okay, and suppose the inner circle has a radius r1 and the outer circle has a radius r2. Correct? Now the current is inside this. Okay, the current is going inside like this. Clear? And the current density is J. It's in uniform current density, obviously. Okay, current density is J. So my question is that what is the magnetic field at a distance r at this point, somewhere in this point? What is the magnetic field here? That is my question. Okay, solve it and tell me the answer. What is the magnetic field for this example? It's a famous question. Every institute used to solve this question. So just tell me, what is the magnetic field for this? See, my health is not good today, so you may feel little less energy. Okay, like yeah, but just calculate the magnetic field at this point. See, what we will do, we will take a loop. Okay, we will take a Ampere's loop and we will consider some direction. Okay, whatever direction you want you can take. I am taking this direction. Okay, I'm taking this direction. So what you will get a closed integration of b dot dl is equal to mu naught into I enclosed. Okay, first you tell me what is J here. J is total current I, okay, divided by pi into r2 square minus r1 square. That is this thing. So what is I enclosed will be in this radius, in this area, sorry, it will be r square minus r1 square divided by I divided by r2 square minus r1 square. And then you have to integrate this. This will become same thing. This will become 2 pi small r. So from here you will get magnetic field is equal to see, pi will cancel out, correct? Yeah, pi will cancel out because that is there. You will get mu naught 2 pi small r r2 square minus r1 square into r square minus r1 square into I. Okay, so that is the answer. Clear? Any doubt till here? Note it down. So you have understand that like it's a very simple. Okay, very simple. It's very simple. Clear? Any doubt till till here? Anyone have a doubt? Simple method, simple step. Whatever we are applying the same thing. Clear? Any doubt? Okay. So we can proceed further. So let us take one example. Have you remember the cavity problems which we have solved in electrostats? Cavity problems. Same approach you have to apply. There we are replacing plus rho minus rho. Here we are replacing plus j minus j. Simple thing. Okay. Just remember plus j minus j. That is what I am saying. If anyone have covered electrostatic properly from me, he will face no problem in the rest of the physics. Not the rest of the chapter, rest of the physics I am saying. Okay. That is a very big statement, but yeah, you will not face any problem. If you have covered from me, that is a question. If you have a covered from me and you have seen my all the lectures and you have covered everything, I am guarantee you that you won't feel any problem in any other chapter, because in first chapter I used to teach 90% of the concept of physics which is going to be used. So that's why in the first chapter I have taken that much of time. Okay. If you have covered first chapter from my side, see this is R, 2R, sorry. This is 2R and this is its center, it is R radius. Now the question is, from a distance 8r from the center, you have to tell the magnetic field. Okay, from a distance 8r from the center, you have to calculate the magnetic field here. That is a question, and all the things are same. The current is inside. And it's a cavity. Okay, remember this. This is a cavity. This is a cavity. For example, you tell me the magnetic field. If you have know the concept, okay, it's very easy for you. Okay, if you know the concept, it's very easy for you how to calculate the magnetic field at any point, or like it's very simple for you. Okay, if you know the concept. What we have to do, we have to replace this whole by plus sigma plus j, then this one with minus j, like that. Whatever I told you the proper method also how to solve this. So let us take let's give a try. Let's you try first, then I will solve. Okay, have you tried? Done? Completed? Okay, so let us see here and match your answer with my answer. Okay, so see, it is, if you see, it is a combination of two spheres. Okay, one bigger sphere, if you see, like it is like this, plus sigma plus j. Okay, it's plus j, correct? It's a plus j, and I am asking you from the center the distance is 8r, and at this point I am talking you the calculating the magnetic field plus, and this is outside, and from the center distance of how much? See, this is 2r, this is r, so it will be 3r. So 8r minus 3r is how much? 5r. From the center the distance is 5r. Are you getting my point? So from the center the distance is 5r. I am asking you to calculate the magnetic field outside. If you see, it is this two, if you combine these two, you will get this one. Are you able to understand? Just I have replaced, if you add these two, you will get this one only. Clear? Now just calculate it. Simple only. What you have to do? Just calculate, just write the value first. Just write the value and calculate it. How will you calculate? What is the magnetic field for this case? Is mu naught I upon 2 pi. What is the R? Eta. Correct. What is the magnetic field for this case? Mu naught I upon 2 pi. What is R? That is 5R. In this case, what is the direction of magnetic field? Just in, well, it's downward. For this case, magnetic field is upward. So just what you have to do for net, D net, you have to subtract. See, for this case the magnetic field is downward, for this case the magnetic field is upward, this case downward, just you have to subtract. Now you have to see which one is bigger. This is bigger, so just subtract this. Mu naught I upon 2 pi R 1 by 5 minus 1 by 8. You subtract, what you will get, that is 3 by 16 580. 3 mu naught pi I 80 pi R, that is B net. Okay, clear. And what is the direction? The net direction will be what? Which one is greater? If you can see which one is greater, this one is greater, so net direction will be upward. Clear? So due to this you will get a magnetic field in this direction, and the value will be, what is the value? 3 mu naught I upon 80 pi R. That is the answer. Clear? That is how we solve the cavity question. Okay, there I have taken 3 illustrations, but here I will take only 1 illustration. Why? Because these things we have covered. Now I can ask you inside also, now I can ask you outside also, surface also, I can take anything. Okay, just you have to understand, yeah, the concept is same, only there is a change in the formula. You have to change the formula, but otherwise the concept will remain same only. Okay, so that is the thing you have to understand. Okay, don't mug up the questions and mug up the things. Just try to understand the concept, because concept understanding is very important as compared to other things. Okay, you have to understand the concept very properly, then it is able to, then you are able to do something. If you don't understand the concept, then it is all thing is waste for you. Clear? Okay, now you have, if you have, we are discussing about cavity. Have you remember the one special case? What is the electric field inside the cavity? What is the electric field inside the cavity? If the distance between the two centers are L, if you have remember that case, I have taken a very special case. We know we have to find, we have got the idea, we have got a concept that it is always constant. Okay, so let us check this. Okay, so suppose this is a center of bigger and this is the center of cavity. The radius of this is given as A, and the distance between them is L, and the radius of this is B. Correct? Now let us take some point in the cavity. Okay, and let us take this as R1 vector, this as R2 vector, this is theta 1, this is theta 2. Correct? Any doubt till here? It is visible or not? Okay, let me draw it properly. It is not visible to you. Sorry, let me draw it. Okay. So I am saying you just take the two centers. The distance between the two centers is like this, and this distance is L, this radius is A, and this radius is B. Correct? Okay, that is the thing which is given. Okay, correct. This is theta 1, theta 2. It is not clear. Let me draw it properly for you, otherwise you won't understand this thing. Okay, so this is the cavity, this is the center, this is the center for this, Okay. Okay. This is radius A. This is the radius B. Okay. Suppose at this point I want to calculate the magnetic field. So what I will do first, the distance is L. This distance between these two is L. Correct. So from here from here to here we are considering a one R1 vector. From here to here we are considering a one R2 vector. Okay, and we are taking this angle theta 1 and this angle theta 2. Correct. Are you getting my point? So if I bring this triangle outside, zoom. Let me zoom this. So if I zoom this, it will be something like this. Okay. Not look like a perfectly, it haven't drawn there perfectly, but in reality you will see that it is something like this. One side is bigger than other side. Yeah. And this is my theta 1. This is my theta 2. Correct. This is R1. This is R2. So what will be this distance? This is R1 cos theta 1 and this is R2 cos theta 2. Correct. It is going like this, it is going like this, and this is going like this. Okay. So I can say R1 cos theta 1 plus R2 cos theta 2 is equal to L vector. L. Correct. Second thing, if you can see properly, this side is common between these two. Correct. This side is common between these two. So we can say that by, and also this angle is 90 degree. So by right angle to hexagon, there is a one something called as a right angle hexagon in a mathematics, by which I can say this this distance, this height for this, and or you can simply understand, just leave that right hand, leave that rule. Simply you can see this side is common between these and for this also. Okay. So what is the height for this? From this triangle, what is the height for this? This is R1 sin theta 1 for first triangle, and for this what is the height? That is R2 sin theta 2. Correct. So R1 sin theta 1 is equal to R2 sin theta 2. That is given as same, but we know R1 and R2 is not same. That is true. We know R1 is not equal to R2. Let us case. Then in that case, if it has to be equal, then theta 1 should be equal to theta 2. That is the only condition it can be. Okay. So, or R1, maybe it's not always true, it can be anything, but yeah, the thing is that there is two theorems come into the picture how I am writing theta 1 is equal to theta 2. First thing, you can see this one side is common between the two triangles. Second thing, this angle is also 90, this angle is also 90. Clear? That is another rule. And third, due to these two rules, we have a something called as a right angle theorem hexagon, which state that if these two conditions are satisfied, then the length of this and the length of this will be same, and from here we can comment that these two angles will be congruent similar angles, not congruent, it's a similar angles, similar triangles. By using right angle hexagon, we can say it is a similar triangle. Okay. If it is a similar triangle, we can say theta 1 theta 2 because should be same. Theta 1 is equal to theta 2 because for a criteria for a similar triangle is the ratio of their sides and the ratio of their angles is some rule is there. So if by using that rule only, we can say that theta 1 should be equal to theta 2. Okay. Okay, sir, we got that much of idea. Or let us take, if it is not same also. Okay, we will consider the worst case. Okay, we will consider the worst case. We don't know. It can be, sir, I am not able to satisfy. You are saying theta 1 is equal to theta 2, but I am not satisfied with this statement. I don't know about that theorem. How I will do? Whether it is necessary theta 1 is equal to theta 2. It is not always possible. Okay, I understand your thing. So let us consider the theta 1 is not equal to theta 2. Let's do it by general method. Okay, let us figure out mathematics behind this. Okay, suppose some student is saying, so no sir, I am not able to understand what you are saying. This much I am understanding. Okay, this side is common for this also, this side is common for this side. So whatever the length calculate for this triangle, the same length will be calculated from this triangle also. Okay, that much is clear for me. Okay, no problem. Now current is inside as we have told earlier. So if I consider the bigger wire, in this case, can you tell me at this point what is a magnetic field? See, the formula is the direction will be like this. So I can say like this, it is like this. If you see properly, you will find that the direction is something like this. It will be perpendicular, let me draw it properly. See, this you have to understand very properly. This angle is theta 1. So what I am saying, it will be something perpendicular to this surface, like this. Okay, it should be perpendicular to this surface. Okay, 90 degree. If it is perpendicular, I will draw a one perpendicular from here. Okay, this is my B1. Okay, this is my B1 from the inner, from the bigger, from bigger. From bigger one. These are the two observations. We have not used any theorem. We have just written the simple observation which we have got from this. Okay. Second thing, if this angle is theta 1, this is 90. This is 90 minus theta 1. Correct. So what is this angle? Total angle is 90. So that means this is also theta 1. Correct. So if this is theta 1, what is the component? So you can see like this. This is the force we have, and this angle is theta 1, and this is B1. Correct. Similarly, for other case, you will consider current outside. You will write it like this. Okay. So for the other case, it will be something like this. Theta 2. Correct. This is theta 2. Correct. From a smaller one. This is B2. Okay, B1, B2. So if you will see, the horizontal component is we are getting B1 cos theta 1 plus B2 cos theta 2, and in vertical we are getting B1 sin theta 1, and this is what? B1 sin theta 2. So if you calculate B per vertical, we have what? What is the value for B vertical? Can you tell me what is the value for B vertical? It is an inside point. So what is a B vertical? B vertical, I will write mu naught J. B vertical is what? R1 by 2. It's not a J vector. Okay, it's a J, current density. Okay, into cos theta 1 plus mu naught J R2 by 2 into cos theta 2. Okay, so from here you will get mu naught J by 2. Now R1 cos theta 1 plus R2 cos theta 2. What is this value? This is L. So is this a constant or a so this is a constant value. You can see properly. This is a constant. Similarly, come to the horizontal case. Now B horizontal. It will be B1 sin theta 1 minus B2 sin theta 2. Now you tell me mu naught J by 2. Again we will get R1 sin theta 1 minus R2 sin theta 2. Now what about this term? This term is equal to 0. So what is B vertical? Sorry, B horizontal is what? 0. Correct. That is the thing. It's a very important result for JEE Advanced. You have to remember that is the magnetic field inside the cavity is 0, and how it is 0, that is a proper proof. I have not used any mathematical theorem. Theorem is available. I can make it theta 1 equal to theta 2 and I can do that. But just for you, so that you are able to understand this relation I have given from the geometry, and by that, using this relation only, I got that result, that magnetic field inside this will be always constant. And what is the direction will be? The direction will be downward. Correct? Any doubt? If you have any doubt, please let me know. If you have any doubt. In cavity, what is the net magnetic field? It will be inside. Any doubt? Any doubt? Okay. Clear? Now let's do another case. See, we have derived the magnetic field due to the solenoid, you have remember. But here we will consider about ideal solenoid. Okay, we cannot derive for practical by the Ampere circuit law. We can only do the derivation for ideal solenoid. Okay, so let us consider the ideal solenoid we have. Okay, the current magnetic field is like this. Okay, okay, so this is dot, means current are coming outside, and this is cross, that is current is going inside, like this, cross sectional view. Now we have to consider loop, and we have to calculate this. I am telling you just for the feeling how to do this, but there is a no need. Okay, we have derived the formula. So how we have to do? See, we have a formula just to tell you that how to apply the Ampere circuital law for the solenoid into I enclosed. So for that, you have to consider a first geometry. So let us consider a geometry. So we will consider a geometry like this. In this case, we will going to consider a geometry like this. Okay, so we will consider a geometry like this. Clear? And for this geometry, we will we will calculate the. Okay, so let us do this. So let us consider the direction for this in this manner. Okay, clear? So let us start doing the derivation. See, we have a 4 surfaces, if you can see properly. Suppose this is A, B, sorry, okay, this is C, this is D. Okay, so first we will do for A to B, okay, B dot dl. Then we do for B to A, B dot dl. And then we do for, and from here only you will understand why I am saying that we can't apply the Ampere circuital law everywhere. From here only you can understand this. B to C, then C to D, B dot dl, and D to A, B dot dl. Correct? So first tell me for A to B. See, the loop direction in this for AB, this is the direction, correct? And what is the direction of dl vector? Dl vector direction in this direction, correct? What is the direction of B dot dl? Means magnetic field. See, magnetic field you can see it is in this direction, and my dl vector is in this direction, correct? So what is the angle between them is 90. So it will become 0. Why? For this case, you will write B dl cos 90 degree plus. Let us consider the length. You can take it as a square of length L. Okay, square length is L. Okay, yes sir. For this C and D, see, in CD is the outside point, correct? So for outside point, what is the magnetic field? For outside case, we know the magnetic field is 0. So that is obviously this term will also become 0, correct? Similarly, what is about CD? CD, it is like this, and the magnetic field is like this, again 90 degree. So this will also become 0 because 90 degree into into I enclosed, that is I. And there are n number of turns are there. So in total n number of turns, what is the current? See, this is the length, na? Number of turns per unit length is small n. So within this length, how much will be the current? So that is n, small ni, correct? It is a small ni, and the length is L for this surface. Because see, what I am trying to say, for this surface it is 0, for this surface only this surface is left now. So in this surface the length is L. So what is the current in that? Mu naught I into, sorry, what is the current in that enclosed? I into whatever the number of turns per unit length into the length of this, so that is L. So that is what the total inside current. Now for this surface only you will get non-zero term, that is AD surface. Magnetic field is opposite, so you will write it as B dot dl. Dl is L into cos 180 degree. If you want you can write, but doesn't matter. Okay, mu naught I and L. So from here you will get B is equal to minus mu naught NL. But let's talk about the magnitude. So magnitude will be simply mu naught Ni. Mu naught Ni. That is a formula, and we know this formula also. The derivation is not important for you. I have just given you as how to apply the Ampere circuital law. This derivation is not important. You have to remember the formula, that is magnetic field is mu naught N into I. Simple case. Clear? This is for solenoid. Any doubt? Any doubt? Okay. I told you there is another case is there, another thing is there in spite of solenoid, that is something called toroid. What is toroid? See, I tell you in very simple language. You take solenoid, okay, and just fold it like this. You take solenoid and just fold it like this. It is a toroid. Sir, what are you saying? Yes, that is the only truth. You have to take the solenoid and fold it. Let me draw it for you, then you will understand what I am trying to say. You have to do nothing, just take the toroid, just take the solenoid and just fold it. Okay. Okay. Clear? And the radiuses are correct. This is called as a toroid. Simply we have taken a solenoid and we fold it like this. Okay. If I draw the cross sectional view, let me draw the cross sectional view for the cross sectional view. Basically, if you see, suppose this distance from here to here is d. and the thing is that this d is very less than r. So that's why you can see I have not taken any inner radius, outer radius. I have written the total radius at capital R. Okay, that is what I have did, because this d is very less than r. Okay, now let us let me draw the cross sectional view for this. Okay, for this I am drawing, I'm not drawing it very big. Okay, I'm drawing it very simply. Okay, so here if you see the current are outside, so we have a dot for this, for this surface we have a dots, and for this surface we have a cross. Correct, and this is my radius, and this distance is d, and d is given as very less than r. Cross sectional view, how? Just I cut it like this. Okay, that is what I have did. Just a minute. Yeah, that is what I have just did. Clear? Okay, so now suppose I have cut it like this as a cross sectional view. Now my question here, what they ask you, they will ask you magnetic field, they will ask you magnetic field in this region. Magnetic field in this region. Okay, in this region R. Okay, because see, if my R is less than capital R, again the magnetic field will be 0. Correct? R less than capital R, the magnetic field will be what? It will be 0. Obviously, for R less than capital R, the magnetic field will be 0. Correct or not? If I take R greater than capital R, then again the magnetic field will be 0. Now you have to think what is the reason? Why? Now you have to tell me the reason. Okay, that I am not going to tell you. If you apply the Ampere circuital law, you will get the reason. Okay, suppose you take some outside loop. Okay, like this. Suppose you take some outside loop like this. Suppose this is outside loop. What is the total current inside this loop? See, I current is coming outward, and I current is also going inside. So what is the total current? 0. The total inside current is 0. So obviously the magnetic field will be 0 outside also. So just that is what I am saying. That is the reason for this. Why? Because the total incoming current and total outgoing current will be 0. Because the total incoming current and outgoing current is 0. Now we have to talk about at distance r, where r is less than capital R and greater than 0. Okay, in this case we have to talk about. Clear? So let us start. For this, what I will do, I will take in a loop, and suppose this loop is like this. Okay, let us take it like this. Wait a minute. Correct. So what will happen if you apply for this surface v dot dl? Mu naught into I enclosed. This is mu naught into I. Magnetic field, what is dl? See, dl, if you will integrate, that is 2 pi r only, that we know. What is mu naught into current is same I, and here we have also defined something called as a number of turns per unit length. that is n, small n, that is capital number of turns divided by 2 pi small r, correct? So if you write for this surface, what is the current? I enclosed is not I, it is something else. You have to tell me first what is that, then I will tell you. First you tell me what is that I, or let us, will that will be I or something else? I have written, but you have to tell me. If it is I, okay, then what is the reason why it is I? And if it is not I, then what is the value? And if what is that value, then you have to also justify me the reason. Basically, whatever the answer you have to give here, you have to justify me what is the reason for this answer. See, the current will be I only. That is true, because I current is coming out and that I current is going inside. So this will be I, no problem. That is I understand this thing. But there are the total number of turn is n now. So it has to be ni. Because this is not from a single turn, it is from a multiple turns. Okay, there are the multiple turns are there now. And suppose the number of turn is n. N is the number of turns. Okay, so that is what I am saying. So it will become b into 2 pi r. So b value you will get mu naught n into I divided by 2 pi into small r. Now what is n by 2 pi r? That is mu naught into n into I. So you can see the magnetic field is same as that of solenoid. The magnetic field of toroid is same as that of solenoid, and that is what I told you. So toroid is nothing, we have just taken the solenoid and just joined it like this. So that is a toroid only, na? So that's why the magnetic field won't change, it will be the same value, that is mu naught n I. Clear? Any doubt till here? If you have a doubt, please let me know and just note it down. Okay, note it down fast. Completed? Clear? Okay, now the last case we are going to discuss. After that our first part will be finished in magnetism, that is and the last case is infinite current carrying sheet. Okay, infinite current carrying sheet. So let us start. Suppose we have a sheet which has an infinite length. The length is of infinite length. And the current is how? You try to understand how this infinite sheet has been placed. It is placed like this. Okay, it is placed like this and it is going up to infinity. Okay, and the current is inside. So for the calculation of magnetic field for this, see, there are the lot of you can say lot of assumptions are there. Okay, if you go to the reality, there are the lot of assumptions. So, but I am not going into that much technicality because it will going to confuse you only. So let us consider in this case the charge which is going inside the surface. Okay, the charge which is inside the surface, it is given as lambda, that is ampere per meter. And suppose we have taken this as a length of 2r. So in this direction the magnetic field will be downward, correct? For this surface the magnetic field will be upward, BB. Now someone will ask the question that why sir you have taken both the value BB, you don't know na whether it it can be B also, or it can be something else also. But that's what I'm saying. There are some experimental observations are there. On that experimental observation, we are taking BB. Okay, to do that experimental observation, and the same A, C, B, D, or you can say it is B and this is C. Correct? Any doubt? Okay. So this is the case, and the direction you can take like this, no issue. And we will write again close integration B dot dl is equal to mu naught into I enclosed, that is I into 2r. Correct? It will be sorry not I into 2r, it will be lambda into 2r. Sorry, my mistake. Lambda into 2r. Now what is B dot dl? You will break it for A to B first. So for A to B, B dot dl from B to C, B dot dl from C to D, B dot dl from D to A, okay, B dot dl. So the magnetic field in this direction, dl vector is also in this direction, it will become 3 times of r into cos 0. Okay, cos 0 is there, no issue. Similarly for this, magnetic field will be at this point. What is the direction of magnetic field? Like this. See, at this point, if you see the magnetic, see, current is going like this. Correct? One minute. Did mistake? Let me check. This is 2r, 2r. Okay. Let me check once. I think there is some mistake. Yeah. See, if you can see properly here, for this surface, it is in this magnetic field will be what? If you see, the magnetic field will be like this, in this direction, correct? And the dl vector is also this direction, so they will be added. But if you see for this surface, the magnetic field will be like this, and dl vector will be also like this, so this will be also added. Okay, no issue, we will do. So this, for this also, B into 2r, or don't write it as r, it can be any length now, because for this side we haven't defined any length. So let us write it as b dl into b dl only. Okay, leave it like this. Then for this surface you will write b dl b dl into cos 0 degree. But remember one thing, this thing and this thing, these two vectors are opposite to each other. This b vector and this b vectors are opposite to each other. So that means there must be one minus sign will be there. Okay, or we can do one thing, you can see one more thing by geometry also. Suppose if I keep my thumb here, or if I want to calculate the magnetic field, what you will get? You will get the magnetic field in this direction, correct? Okay, where horizontal component will be added and vertical component will be subtracted. Okay, so you will get the net magnetic field in the horizontal direction only, because you can see this is opposite to each other, no? So they will cancel out each other. So for these two surfaces you will get 0. That I can directly say by the geometry also. Okay, by the geometry also. For these two surfaces you will get the 0. Net magnetic field you will get in the horizontal direction only. That is true. Why? Suppose at the at this point I want to calculate. So the direction will be like this, correct? It will have a horizontal and vertical component. Similarly, for this surface, if I want to calculate it, the direction will be like this, okay, like this. Okay, so there will be horizontal and vertical component. So vertical component will going to be cancel out. Okay, only we will add up the horizontal component with each other. So that is why I can say that due to this and this two, because if I am taking this as positive value, this I have to take negative value, because this b is positive, then this b has to be negative, so automatically it will become 0. Okay, these two will become 0. Only we will left with these two surface, and that is nothing but b into 2r plus b into 2r. Okay, and that will be mu naught lambda by 2r. So 2r will become 2r will cancel out. You will get b is equal to mu naught lambda by 2. That is a constant. But remember, the direction is horizontal. The direction is, remember, the direction is like this. This is b net. Similarly, this is b net. This is the direction of b naught. There is no magnetic field in the vertical direction. Why? Because they are getting cancelled out. Because it is an experimental thing. Okay, it's not a proper derivation is there. There are a lot of experimental results. After that, we have got this derivation. But remember that there will be no magnetic field in this case. You will not get a vertical magnetic field. You will get a only net magnetic field in the horizontal direction for the infinite sheet, long sheet. Only the magnetic field will be in the horizontal direction. So that's why I have taken these two value will be 0. Okay, and I have tried to explain you that, try to give you the reason also. I have tried it because these two values are opposite to each other and the values are same. So I have to write a negative sign. I have to write one of them with a negative sign. In spite of that, that the angle between these two dot products are 0. I have to write it one of them as a negative. So they will cancel out each other. The net value you will get only in the horizontal direction only. And that is the value is constant, that is mu naught lambda by 2. If you remember, in the infinite sheet also, the charge sheet also, we have got a constant value, which is a horizontal electric field. There is no vertical component, correct? So it is exactly same like that. Only the value has been changed, that is sigma. There the formula is sigma by 2 epsilon naught. Here the formula is mu naught lambda by 2. Clear? Any doubt till here? Please let me know. I hope everyone has understand those the concept which I have tried to explain you, because it is very important to most of the students don't understand. Okay, so I hope you have understand this thing. Have you understand this thing? Is there is any doubt, any percent doubt you have, please let me know. Any doubt is there? No doubt? Clear? Okay. So okay, in today's class we have finished the complete discussion on the magnetic field. Now there is no discussion left on the magnetic field. We have calculated the magnetic field for all the types of geometries and for all the cases. Now in the next section we are going to start the discussion on the, we will start the discussion on the force calculation. Okay, and we will see the lot of things in force calculation. This is what we have did in the whole session. We have defined everything. Okay, and okay, I have given some question to you. Let me check is there is any homework for you. Okay, I have solved this. Okay, so yeah, so thank you. I hope you have enjoyed this session and you have learned a lot. If you have liked this session, please like it, share it and subscribe it, and have a nice day. Thank you.